Swayam Prabha. Digital India. Educated India.
We continue our discussion on modern trends in refractory. Some I already discussed in the previous lecture. Today I will be discussing on monolithic refractory. What is a monolithic refractory? Monolithic refractory is the name given to all unshaped refractory materials. That is, monolithic refractory is the name given to all unshaped refractory materials. They are not like bricks as we have seen earlier, but they are unshaped refractory materials. These materials, they are installed in some form of suspension that ultimately harden to form a solid mass. Second, these materials are installed in some form of suspension that ultimately hardens to form a solid mass. That means these monolithic refractory material, they are in fact in a powder form, and depending on the design of the reactor, these monolithic refractory material, they are installed right at the spot. They are unshaped one, and they can be given to any shape depending on the requirement of the reactor. So, the types which are available, they are in fact castables. That means they can be cast into the shape which is desired for a particular requirement of the reactor. Remember, they are not like bricks. The shape of the brick is fixed. So, that is an important thing. So, in fact, these monolithic refractory consist of mixtures of coarse and fine grained refractory material. A proper proportioning of coarse and fine is important, because when this is cast, then the material has to dry of sufficient strength. So, a proper proportioning of coarse and fine size in the mix is important. Second, this is gelled by means of a binder. That means a binder has to be added so that they can form a mass which can flow and which can be casted. Naturally, when it is mixed with a binder, the material will be in the green form. Then the common binder which is used is Al2O3. Now, once this mixture has become ready, then comes the installation. Now, installation, we have two types of these castables. One is the free flow castable, free flow castables, and these free flow castables have low water content, and another method of installation is by gunning. That is, the mixture is allowed to flow through a gun at a particular pressure. Now, we have say three different types of mixture could be. One will be plastic refractories, then ramming refractories, and patching refractories. Now, here say material plus binder this mixture which has been formed through material and addition of a binder should have sufficient plasticity so that it can be rammed at a particular place. What I want to say is that this monolithic refractory which are unshaped material, they are used for different purposes. One of the purpose, you want to say refractory line a reactor, could be a torpedo vessel, could be LD converter, could be electric arc furnace, some region. Say you do not want to monolithic refractory everywhere at some particular place. You want to ram the mass, as for example, you must have seen in electric arc furnace or in torpedo vessel, where I have said that the mouth of the torpedo vessel is rammed by a monolithic mass. Similarly, in case of BOF, similarly in case of electric arc furnace, the bottom of the vessel, they are many times rammed in order to achieve a high lining life. Third could be patching. Say for example, once the heat is over, certain areas are worn during the heat time. Then once the heat is tapped, those areas are identified, and with the help of monolithic refractory, they are patched. So, they also have a patching type of refractory. Then also we have coating refractory. For coating purposes, so to coat the working lining for several reasons. You want to coat the refractory lining so that the phases do not adhere to the wall of the refractory lining. Then we have refractory mortars. They are in fact finely ground refractory material which are then mixed to form a paste used for laying and bonding shaped bricks. So, this is the refractory mortars. Now, say insulating castables, these insulating castables, their main objective is to block the heat transferred from the vessel to the environment. So, their main objective is to provide insulation. So, they are used for cold phase insulation. These insulating castables, they are made from lightweight aggregates like vermiculite, bubble alumina and clay, because the insulating castable should have a low thermal conductivity and low density. Why it should have low thermal conductivity? Because thermal conductivity is a property which allows heat from the reactor to be transferred to the surrounding or not. How fast or how quick the heat will be transferred, that will be determined by the thermal conductivity of the material. So, if the monolithic material is to have an insulating property, then it must be of low thermal conductivity, and low thermal conductivity is obtained by having a porous mass. So, naturally they will also have the low density. Now, since this monolithic refractory, they are used by mixing with a binder and water in a green state, a shape is being created either for ramming or for pitching. So, in all the cases it has to be dried. If it is not dry, then water will evolve, and as a result a problem would be there during the operation. So, the largest problem with the use of monolithic refractories, the problem with the use of monolithic refractory, one of the problem is long duration time. Long duration time, because the water which you have mixed, in order a solid material can flow and take the shape of the reactor, or can be rammed or can be patched, it has water in it, it has binder in it, so all have to be removed before heat can be operated. So, this water, it will have a sort of steam explosion. That means a large amount of steam will be evolved. So, these two problems, they require a sort of steam explosion free drying technique. So, what you require is that steam explosion free drying technique. Now, for your information, monolithic refractory are finding a wide application in the steel industry. Now, this is regard the monolithic refractory. Now, one of the important thing in controlling the furnaces is that one must be able to measure the lining thickness. One must be able to measure lining thickness. Inspection is also important. There are various technologies are there which can measure the profile of the lining. For example, eddy current, technology of detecting brick cracks by elastic shock waves, they are all in commercial application. Now, let us see some of the repairing methods or maintenance method. So, as such I will put the next title is furnace refractory maintenance. Furnace refractory maintenance. Slag splashing. This was developed around 15 years ago, and today some plants they claim that they have achieved around 60,000 heats in one particular vessel by using slag splashing technology. The details of it I had already explained to you when I was explaining the splash technology in BOF steel making. Here I will just put in short. After steel tapping, some amount of slag is retained in the vessel, This slag is conditioned by adding FeO and MgO. If FeO and MgO contents are less, then nitrogen is blown through a lance. As a result of blowing of oxygen through a lance, a jet of nitrogen impinges on the slag surface. On account of this impinging action of the jet, the slag splashes around the walls of the converter, and as a result of the splashing, the slag very beautifully adheres on the lining of the wall. Because the slag has FeO and MgO, so FeO provides the adhesion behavior and MgO provides the so called high temperature phase. So, this is in short the slag splashing and its application for BOF steel making or for maintenance. For that purpose, I mean, wherever you have a slag, this technology should be able to work, because all that you require, the slag which is retained, which is available to you, you use it for splashing, and hence the lining life of the converter can be increased. Now, here one of the important case is that if the slag is more than the required, then the excess amount of slag, it builds in the bottom. So, it may destroy the bottom instead of giving you the benefits. Therefore, excess slag has to be poured off before charging. The problems with this slag coating is, one of the problem is the mouth skull formation. One of the problem is mouth skull formation. I am referring with reference to BOF steel making, because slag splashing has been developed for BOF steel making. So, at the mouth, when the slag splashes, the slag has a lower melting point, so immediately it deposits on the mouth of the converter, and hence there is a formation of the skull, and because it is a highly viscous, it has to be removed. That is one important issue, and another important issue is the sculling of the lance. In slag splashing, one more thing I would like to mention, when slag splashing is used for top and bottom blowing converter, then in that converter we have bottom tuyers. These bottom tuyers should be free. So, if you use the slag for splashing, then one must take sufficient care so that the slag does not block the bottom tuyers. So, third issue could be the blocking of the bottom tuyer should be avoided. So, this is in short about slag splashing. Another is that slag coating and slag washing. Now, here what is done is that you retain the slag, condition it with dolomite to cool the slag and to increase its adhesive properties. Then the vessel is rocked in motion so that the slag splashes all around. So, this is also one of the repair techniques. Then the third is hot patching. Third is hot patching. Now, in the hot patching, the self-flowing refractory mixes enables precise maintenance of the scrap preheat zone, taping pad and bottom joint. This is for the hot patching, wherever between the heat if there is a problem, then this hot patching can be done. Another important repairing technique is that of gunning. Now, here for example, flame gunning is used. Flame gunning is used. Now, this flame gunning involves simultaneous melting of a refractory powder and gunning at the hot surface. That means, the melting of the refractory material and its injection at high speed to the area where repairing is required, it is done simultaneously. Now, since the gun repair material is dense and fused directly on the hot surface, so excellent result in the life of the lining is obtained, for example, in LD converter. So, this is about the flame gunning. Now, another important process is called short crating. Short crating. In this particular process, the castables are pneumatically projected at high velocity onto a surface. I will write for you. This is the process by which castables are pneumatically projected at high velocity on to a surface. That means, here the melting and gunning both are simultaneously achieved. So, the advantages will be of course much better. Now, here refractory materials are designed for self flow, that is important. So, I will just draw a flow sheet. How does it work? For example, we have a material here, put a material, some amount of water, both are mixed in the so called mixer, and this mixer is then taken to a pump, and from the pump this mixture flows through a nozzle. So, this is a nozzle. Now, here we have a compressor. This is a compressor. This is a vessel. This is a vessel. Now, in this vessel some materials are added. So, added materials, and this is also going to the nozzle. So, that is the way in which the short crating method works. Now, the material pump that is here, there are two types. One is the piston type of pump, and another it works at a speed of 100 kg per minute. Mixer capacity could be around 500 kg per batch. Air compressor be of the order of 11 meter cube per minute capacity of the compressor is required. So, this is in short about the modern trends or emerging trends in refractory. Now, if some of you who are interested in the refractory and do some work, then I will just outline future issues in refractory technology. One would be important, what is required to increase the durability of refractory. Durability of refractory, where in critical areas, for example, pouring nozzle, side dams, and such critical areas which are prone to wear, the durability of refractory is an important issue. So, future attempts will be directed how to increase the durability of refractory by having better quality refractory. Another important thing, steel making technology goes together with refractory technology. As in the steel making lecture, you must have heard post combustion is one of the important technique to increase the energy efficiency of the BOF or electric arc furnace. But imagine the temperature which would be created in the freeboard of the BOF or EAF will be very high. So, accordingly super high temperature refractory would be required. Super high temperature refractory will be required. Mind you, unless these refractory are available, one cannot implement the post combustion technology in electric arc furnace or BOF. That is a very important, and in this connection also the energy optimizing furnace where also very high temperature is created because of post combustion in the furnace. So, the refractory development would be an important issue. Third is that we have to develop the processing technology, and here super fine powder processing technology, super fine powder processing technology is also required to be developed. Fourth, that is important, the development of monolithic refractory in steel making or in refining furnaces require to automate bricklaying and intelligent repair. So, what will be required is that automation of bricklaying and intelligent repair. Now, since monolithic refractory is not used in the entire vessel, only in the certain proportions. So, accordingly bricklaying methods has to be developed. Another important thing is the development of nanotech refractories. Nanotech refractory. Thermal shock resistance and corrosion resistance require opposite characteristics. So, nanotech refractory satisfy both. Nanotech particle they act in two ways. First, they consist of nanosphere, nanospheres and improve properties like elasticity and strength. And second, control of molecular structure, as the particles have many small pores of several hundred nanometers. So, these are some of the future issues. Those who want to go in detail, I have given the references at the end of this lecture, so one can follow those references. Now, with this I will proceed now to the next title, that is the clean steel. Naturally, the question is, what is clean steel? Clean steel refers to number of inclusions per ton of steel. Clean steel refers to number of inclusions per ton of steel. depending on the diameter of the inclusion and the dissolved oxygen content of steel, number of inclusions may vary from 10 to the power 12 to 10 to the power 15 per ton of steel. What does it mean? That means it is not possible to produce a steel which is free from inclusions. All that we can try is to minimize their numbers. Therefore, we can talk about a cleaner steel, but not in the literary meaning of clean steel, which by definition would be a steel with zero inclusion content, which is not possible. So, what we will be talking? We will be talking how to have a cleaner and cleaner and cleaner steel with reference to the number of inclusions. Now, these inclusions, they affect the mechanical properties of steel. As you recall, when I was dealing with my first lecture on steel and its classification, I did mention about the role of inclusions. So, from the point of view of applications, it is important to know what is an inclusion, how it affects the mechanical properties, how their sources can be controlled. Let us see one by one. So, first of all, we will say how we assess the cleanliness. So, first I will put cleanliness assessment. Cleanliness assessment. Now, in assessment of steel cleanliness, what is important? Type of inclusion, morphology, morphology of inclusion, size and size distribution are important. Size and size distribution, and it is also important where the inclusion is located, that is location of inclusion. Location of inclusions. Now, let us say what is the type. An inclusion in fact is a chemical compound of metal plus non-metal, and hence it is termed non-metallic inclusions. What are the different types of inclusion? One of the type is oxides. For example, Al2O3, MnO, FeO, SiO2, or for example, we may have FeO, SiO2, then MnO, SiO2, or CaO, Al2O3. These inclusions, they are termed simple type of inclusions, whereas these inclusions, they are termed complex inclusions. They are termed complex inclusions because more than two oxides. Another example, sulfides. The examples of sulfides are, for example, FeS, calcium sulfide, MnS, or could be even complex type of sulfides, FeS, MnS, or CAS, MnS, or whatever. Then we have nitrites. Then we have nitrites, for example, titanium nitride, ALN, of course depending on the availability of titanium or aluminum, then vanadium nitride and boron nitride depending on the addition of these elements and the concentration of each to form an inclusion. Then we have carbonitrides, carbonitrides for example of titanium, molybdenum, niobium carbonitrides. We can also have oxysulfides, and for example MnS, MnO, CAS, Al2O3 or in whatever combination, because in fact the impurity elements which are present in the steel, carbon, sulfur, phosphorus, nitrogen, oxygen, hydrogen and dissolved oxygen and other alloying elements, depending on the concentration they will form a compound with metal and non-metal. About the morphology, there could be different shapes. Say one of the shape for example is a globular shape, Now globular shape is a preferred shape, it does not have a bad influence on the properties of steel. Another is a spherical shape inclusion, that forms in a liquid state at low contents of aluminum. Manganese sulfides and oxysulfide inclusions, they formed during solidification in the interdendritic region are also globular in nature. So that means the globular nature of inclusions, they are little less harmful. That depends upon where they form, because inclusion can form either during solidification or during taping or teaming of steel. Another shape is a platelet shape. Say for example, the deoxidized steel with aluminum, it contains manganese sulfide and oxysulfide in the form of thin film located at the grain boundaries. Now if the inclusion is located at the grain boundary, then they weaken the grain boundary and will affect the mechanical properties in the hot state, and that is called hot shortness. So that means these type of inclusions, that is the platelet shape which are appearing at the grain boundary, they are more harmful than if the inclusion is present in the matrix. Another shape is a dendritic shape. Now by the nature of the dendrites, it is a tree like shape, and the sharp edges and corners, they induce the local stress concentration, and which considerably decreases the ductility, toughness and fatigue properties. So dendritic shape, I just put few words from here, that is they have sharp edges, and corners of dendrites, they may cause local concentration of stress, and as a result they affect the so called the mechanical properties like ductility, like toughness and fatigue properties. Now another shape is a polyhedral shape. Polyhedral shape, they are less harmful than dendritic shape. Another important property is a size and size distribution. Size and size distribution. Say we can have macro inclusions, the larger size, and we may have micro inclusions. Larger size inclusions, that is the macro inclusions, they are very harmful as compared to micro sized inclusion. In fact, sometimes it is preferred to have micro sized inclusion in the steel. Why? Because say micro size inclusion it may be beneficial. Why? It can restrict grain growth. It can restrict grain growth. When? For processing of the steel material, the material is heated below the melting point of the steel, normally 1100 to 1200 degrees Celsius, that is in the solid state. So, there the grain can grow, and larger size grains, they affect the mechanical properties as compared to fine size grains. So, therefore, if the micro size inclusions they are present, they can influence the grain growth, they can restrict the grain growth, so that grain does not grow during heating for example, for deformation processing or for heat treatment or whatever the treatment is required to create a product of a particular property. Second important point that is in favor of micro inclusions is that increase in yield strength, it increases yield strength and hardness. Naturally, they are micro sized inclusions and they are distributed well in the matrix. So, you can imagine the steel has become a composite material. Matrix with the oxides, that is a composite material. So, it has a better property. The only important point in case of inclusions that they should be of fine size and distributed well within the matrix, then one may have a very different properties than if they are located on the grain boundary. Third micro inclusion can do is that they act as a nuclei, for precipitation of carbides and nitrides. So, in short, what I wanted to say is that not all sized inclusions are harmful. So, a statement that inclusions are always harmful has to be modified in terms of what is the size of the inclusion we are referring. If the inclusion size is very small, say micro size inclusion, then you may not like to remove them because they will be beneficial during the process of heating or reheating the steel to create these special properties. So, that is an important thing over here. So, what is important from here is that it is the distribution of inclusion is also important. If the inclusions are present at the grain boundary and if the inclusions are present well distributed in the matrix, then they will have a altogether different influence on the properties of steel. Now, let us see the inclusions and mechanical properties. Now, inclusions have very different physical properties than the steel matrix. For example, thermal expansion. For example, thermal expansion. So, inclusions like calcium oxide, Al2O, CaO, Al2O3, Al2O3, spinels, nitrides and silicates, they have thermal expansion, lower than the matrix, What they will do? On heating, these inclusions have lower thermal expansion as compared to the matrix. So, internal stresses of thermal origin will develop, and these type of inclusions are detrimental to fatigue properties. Remember, the detrimental to fatigue properties arises from those type of inclusions which have thermal coefficient lower than the matrix. You can imagine also how this will happen. When you heat it, one will expand larger, another will expand less larger. So, that is important. Another extreme is that, say for example, inclusions like manganese sulphide, calcium sulphide, MgO and CaO have thermal expansion, greater than the matrix, So, void or parting of matrix can occur, and these void can act as cracks. So, this is one of the important physical property difference between the inclusion and the matrix. Another difference is deformability. Some inclusions are highly deformable and some inclusions are less deformable. For example, inclusions like Al2O3 or calcium aluminate, say CaOAl2O3, they are undeformable at all temperatures used for deformation. So, they will crack. On the contrary, manganese sulphide is highly deformable up to about 1000 degrees Celsius, and similarly FeO, MnO are plastic at room temperature, but gradually lose plasticity above 400 degrees Celsius. Inclusions like silicates are deformable at high temperature, but undeformable at room temperature. So, what I wanted to say from here is, during hot deformation processing, which type of inclusion is present, that is an important. Inclusions like MnS will not be having any problem, but inclusions like Al2O3 or calcium aluminate, because they are not deformable at high temperature, so immediately that will crack. Third important property is that of the melting point. The melting point of all the inclusions except alumina, pure alumina, is most of the inclusions is lower than the steel matrix. So, what I want to conclude from here is that inclusion matrix do not match with each other. I repeat again, because of the very difference in their physical properties like thermal expansion, like deformability, the inclusion which is present in the matrix, it does not match at all with the matrix. So, this particular phenomena is very important depending upon what is the thermal expansion or what is the deformability and so on, the crack or local stress concentration will be developed, and on deformation or on providing a load they may crack at each other. The further aspects we will take in the next lecture.